previous lecture, we discussed transport through double quantum dot in the low bias regime. And what we saw was in the gate voltage space VG1 and VG2, those are the gate voltages for dot 1 and dot 2 respectively. There are hexagonally arranged points where the current is non-zero. Everywhere else the current is zero, and that we call the charging diagram or the stability diagram for the double quantum dot. So in this lecture we will inspect the transport. Then you have a high bias or large source strength bias across the double quantum dot, and that what you would find is these hexagonally arranged points would expand into triangular regions, which are usually referred as bias triangles. Then later in this lecture we look into few electron double quantum dot systems, singlet and triplet states, and finish it with a phenomenon called spin blockade, which is a manifestation of Pauli exclusion principle in the transport properties of quantum dot systems. All right. Let us quickly review what we had in the previous lecture. So we are interested in the transport where the mu s and mu d, those are the source and drain chemical potentials. Mu1 and mu2, the chemical potentials of the electrochemical potentials of the dot 1 and dot 2. So these are the electrochemical potentials which are pretty close, but the overall source strain bias applied across the dot is pretty close to zero. It's a low bias regime. And what we found is in the VG1, VG2 space, you have hexagonally arranged points of non-zero current. And inside the hexagons, the current is zero. And we also found that the charge configuration inside the hexagon is constant n and m, where this nm could be any number starting from 0. When it is 0, 0, there are no excess electrons on either of the dots. Okay, and when you go towards the positive x direction, that is when you increase the VG1, you are pulling the levels of the dot 1, and that dot 1 will get more and more electrons pulled in. We can see that 1, 0, 2, 0, 3, 0, 4, 0, and so on. And if you go vertically, you have the VG2 increasing. That means you are pulling the levels of the quantum dot 2, then that dot is going to get filled with electrons in a sequential manner. That is 0, 0, 0, 1, 0, 2, 0, 3, and so on. So inside the hexagonal region, the charge is stable or charge cannot change, and the transport is blocked. And the transport is allowed only at these corners of the hexagon. Those are the triple points. You have the electron triple point and the hole triple point, these two. Triple point means 3 charge configurations are degenerate. And when you cross any of these lines, you can see the charge configuration is going to change, but there is no transport there. For example, these two, 3, 0 and 3, 1, and along this boundary, the 3, 1 and 3, 0 are degenerate. Okay. Similarly, along this boundary, 1, 0 and 2, 0 are degenerate. across this boundary 1, 1 and 2, 0 are degenerate in this boundary, and so on. Okay, and from the geometry of these hexagons you can extract capacitance associated with various gates of the dot. That also we discussed. And this is an experimental charge stability diagram for a carbon nanotube double quantum dot, where you have a carbon nanotube and 2 quantum dots are realized in a carbon nanotube. And as we discussed, there are hexagonal regions, and the current, non-zero current, is only there at these corners of the hexagon. Those are the triple points. Okay. So that is summary what we have so far. That is, inside the hexagon, the charge state is stable. The number of electrons cannot change, and current is possible only at the edges of these hexagons. Those are the triple points where 3 charge states are degenerate, by which you are getting a current flow system in a sequential manner. All right. Now, that is a summary so far. Now let us look at what happens when you have slightly higher bias on the system. Let's assume that you have this configuration where mu drain is at a higher energy compared to mu s. That is, you have a positive bias on the source and you have a negative bias on the drain. Or you can say that you have a positive bias with refer to the drain on the source. Then the charge transport happens by the flow of electrons from a region of higher energy to towards a region of lower energy. Okay. So what that means is, for the transport to happen, you need mu2, that is the electrochemical potential or the available energy state of the dot 2 should be less than or equal to mu d. Mu2 is the electrochemical potential dot 2 and mu1 is that of the dot 1. So mu1 should be less than or equal to mu2. Then only this electron in the second dot can tunnel to the first dot, and eventually mu1 is the electrochemical potential of the dot 1. That should be more than or equal to mu s, or mu s should be less than or equal to mu1. Then only this electron can finally reach the mu s. What this says is, these situations, these equalities are the limiting cases for the current to flow through. Mu1 equal to mu s. The moment mu1 is less than mu s, what that means is this level is below the mu s, then the electron which is in that state is Coulomb blockaded, or that electron cannot go to source side here because these states are already full. Okay, there is no vacancy there. Similarly, mu2 should be more than mu1, then only the electron can go here. If the mu2 is less than mu1, then that electron will get locked here. This cannot go here, this cannot go here. It is locked. That means dot 2 is in Coulomb blockade. Okay. So these 3 conditions need to be satisfied simultaneously for the current to flow through the system. Okay. And these are represented by these energy level diagrams here. These are 3 equalities. And we also learned that the directions in the charge stability diagram for a double dot represent certain energy level alignment with either the source or the drain or each other. Okay. For example, if you move along this direction, this arm of the hexagon, that means you are varying only the dot 2 energy level, whereas dot 1 is in resonance with the source. Similarly, if you are moving along this slope, the blue line here, that means your dot 2 is in resonance with the drain and you are varying only the source level. But if you are moving along this teal or the blue line, light blue line, then these 2 levels are in resonance. Okay, they always move together. So these three slopes are here, okay? And whatever the conditions that we discuss here, in one case mu2 is resonant with the drain, second case mu1 is equal to mu2, and third case is mu s is mu1. These are the three conditions, and these lines are the limiting cases for these conditions. Okay. What that means is, for a current to flow through the system, you need to have these three conditions met, or the area in the VG1, VG2 space enclosed by these three satisfy these three conditions together. So this blue line, that is mu2 is equal to mu t, the area above this, okay? The area below mu2 equal to mu t is correspond to basically the second dot level above this drain side, because this is a more negative side for mu2, for VG2. That means this level goes above this V, then no transport is going to happen because that level is not available. So area above this level, above this line, and similarly mu1 is equal to mu s, the area left to this line, okay? That means if area right of this line correspond to mu1 less than mu s, because the gate VG1 is getting more positive. That means this level goes below the source side. That means that is a Coulomb blockade region for that dot. So no transport is going to happen this side. So now we have two conditions: area above this, area left this line, and now the third condition is mu1 equal to mu2. That means the moment mu1 is greater than mu2, okay, mu1 is greater than mu2, the transport is going to get blocked again, because this is going to fall, the dot 2 will be blockaded, no transport will happen. That means mu2 should be, the gate should be more negative or less positive. What that means is the area in this region, okay? So now we have three conditions: mu2 is equal to mu d, this line; mu1 is equal to mu s, this line to the left, to the above this line, and to the right of this line. So you have these three conditions met together. That represents the region where you are going to have non-zero current in this biasing condition. And I have represented schematically these three energy levels corresponding to the corners of this triangle. So you have three lines, non-parallel lines, and the area enclosed between would be a triangle. That is what you are going to get when you apply bias with a non-zero current, and that is the origin of the term bias triangles, because when you apply bias, you get triangular regions of non-zero current. Okay. Now, if you reverse the bias, you're going to get regions of no current in the opposite direction. Okay. And that is represented by the triangles which is pointed upwards. These triangles are pointed downwards here, and these triangles are pointed upwards. And the relative alignment of this triangle is shown here. So this is for forward bias, this is for forward bias, and this is for reverse bias. Reverse bias. Okay. And this is an experimental data showing the orientation of this triangle taken from this work. For positive bias, you are getting the upward facing triangles, and for negative bias, you are getting this downward facing triangle. And this positive and negative are just relative, because that depends upon what side they have assumed drain and which side they have assumed source. So the positive side and negative side may not match through all the publications or all the work. That is just a convention. Which side you have assumed positive, which side you have assumed negative. All right. So this is the physics of the bias triangle. The summary: when you apply bias, you get triangular regions of no current. These points which you had no current initially when you had zero bias expand into triangular region. Okay, and this diagram represents the relative orientation of this triangle. You will have triangle facing upwards for one bias, and if you reverse the bias, you will get this triangle facing downwards. Okay, and this is what you would find when you apply bias through a tunnel coupled double quantum dot system. Now, when you move to few electron double quantum dot system, you need to worry about the single particle states and their interactions with each other. So these double quantum dot systems are artificial molecules. So you know that the single quantum dots in the few electron regime are artificial atoms. So when you take two atoms and bring it close together and couple each other, then you get a molecule. You have two atoms, you have diatomic molecule. Okay, so these double quantum dot systems are artificial molecules. They are tunable two-level systems. So you have the atomic state, the energy level in each dot, which you can tune by tuning the gate voltages. So you can tune the energy difference between these two, and you can play around with various device parameters. Basically, what we got now is you have an atom where you can tune the energy levels. Naturally, you cannot do that because naturally the atomic energy levels are rigid. So you don't have much freedom to tune those energy levels. But here you have artificial atoms where every feature of that is tunable. Energy levels, energy spacing, size of the atom, and all these things. Interaction between the atoms, which you cannot tune much when you have a natural atom. Okay. So in this diagram, what we are seeing is you have the E1 and E2 are the energy levels of the isolated atom. And when you bring together, when you make them couple, you'll have the tunnel coupling, which is marked here by 2T12, and the resultant system will have energies EA and EP. So the Hamiltonian of the isolated dots are H0, phi1 and phi2 are the wave function. H0 will have an eigenvalue of E1 and for phi1 state, and E2 for the phi2 state for the uncoupled system. So we can think that these two dots are far away. They are not coupled. When you bring them together, the resultant wave function are represented by psi A and psi B. Okay. So these are the wave functions, and these are the new energies EB and EA, where those are given by EM plus 1 by 4 delta E square T12 square, and the bonding energy, and the EA is anti-bonding energy and VB is a bonding energy that you will see very soon why I am calling them bonding and anti-bonding in a minute. Okay, so EM is EM minus square root of 1 by 4 delta E square plus T12 square. Okay, and these are very simple mathematics which you have worked on, I'm pretty sure you have worked through this in some of the lectures in the chemistry or even quantum mechanics. Okay, and this psi B and psi A are the wave functions for bonding and anti-bonding. And the psi b and psi a are actually linear combination of phi 1 and phi 2, okay, with some phase term. And the theta is given by this relation. And the energy difference for the coupled system, EA minus EB, is given by this. So you can see that the energy difference is same as delta E, the initial energy difference, when it is not coupled, when you take T12 is 0. When T12 goes 0, that means these dots are far apart. Delta E star becomes delta E. Okay, that's what you have. So the tunnel coupling between the two dots or two systems is what's going to give you the new energy states or new energy distribution. Okay, this is the this is the overview of the molecular states what we are discussing when you bring two dots and couple them together. Now, as I told, let's consider you have two dots, okay, dot 1 and dot 2. Okay, this is dot 1 and dot 2, and E1 and E2 are their isolated energy levels. When you bring them closer, you have a tunnel coupling, say 2T. Now remember, even in this case, for this discussion, I have assumed that E1 is equal to E2. These two levels are same. That means the detuning between the two dots is 0. When they are not coupled, we know that they are far apart. E1 and E2 are same. Okay. When you bring them closer, because of tunnel coupling, you get anti-crossing of these two states, these two levels, or you will get two separate energy levels, EA and EB. And the separation between E and EB is a function of tunnel coupling, and that you can see from here. This says delta E is your original spacing, which is 0 in our case, because we have assumed E1 and E2 are same, and 2T1 is tunnel coupling. That is the only thing which is going to contribute to the energy difference between the resultant states. Okay, and this tunnel coupling is a function of the distance. When they are far apart, there is no interaction, the coupling is 0. When you bring it closer and closer and closer, you will have, they'll interact, and you can see that these two levels will grow, out each other, so grow out of each other, and you will get two states. One is the EA, the anti-bonding state, and EB is the bonding state. So that is the chemistry nomenclature. So for us, what we consider is one is single state and one is a triple state. For a common dot, that is the general terminology. You have a single state, which is given by the relation up down minus down up by root 2 here. Okay, this is single state. Okay, up down minus down up. The single state. There is only one state. Okay, and you have also an antisymmetric state, a symmetric state. That is what you are going to get when you do this. Okay, so now you have single state, and you also have a triple state. That means there are three states degenerate, three states with the same energy. That is T11, up up, down down, and down up plus up down by 2. Okay, these are three states. And this splitting between these singlet and triplet states is not really high for a double quantum dot system, for a 1-1 state, because they are still in the same orbital. The splitting is decided by the tunnel coupling. And tunnel coupling in these systems are not really large. They are like few tens of microelectron volt the maximum. So that would be the splitting between the singlet and triplet state that you are going to experience. Okay. So what we are saying is the singlet triplet splitting for a 2-electron double quantum dot is small. It's not really high. It's not zero. We can measure it, and that is one of the key knob that you need to turn to do the quantum computation between the singlet and triplet states. Because of the exchange, which this part I'm not going to go in detail here, just I want to mention for completeness. Exchange, the charge distribution for a single state and charge distribution for a triplet state, that means 1-1 single state and 1-1 triplet state. That means this state and this state. Okay, this is the single state and this is the triplet state I am referring to. These two states slightly different. For a single state, there is a little bit big for charge distribution towards one of the dot. Okay, and for a triplet state, it is perfectly symmetric, the charge distribution. Okay, but the energy levels of the singlet and triplet states are pretty close for a double quantum dot system with zero detuning. But you can also have the singlet and triplet state for a 2-electron single quantum dot, as shown here. Okay. So here you have 2 electrons in a single dot. Again, the singlet and triplet states are given by the same notation, but these are 0-2 triplet state. The reason I am calling 0-2 because you are considering only the dot 2 in this case, the right side dot. Dot 1 I am not worried about. So the situation that I am comparing is the energy levels of a few electron double quantum dot when you have 2 electrons in the system, 1 and 1 on each dot. That is what we discussed so far. This is this case 1-1 singlet and 1-1 triplet. That is, you have 1 electron in each dot. Second case is 0-2. That means again you have 2 electrons in the system, but both of those electrons are in the same dot. That is the dot 2. Okay, in this case you can also have dot 1. The discussion is invariant whether we have 2 electrons in one dot or in the right dot or left dot. When you have 2 electrons in the same dot, in this case say 0-2, okay, let me say that configuration as 0-2, okay, you get these 4 states. You have 0-2 singlet state and you have these 3 triplet states. But in this case, remember, they are the same dot. So these are different orbitals. Singlet and triplet are different orbitals. So the singlet triplet spacing or splitting is really high. That is equal to the orbital energy. And when the spin states are degenerate, that is when in the absence of any magnetic field, these 3 states would have the same energy. These 3 states will have the same energy in the absence of any magnetic field. And the singlet triplet spacing is really large for a single dot, because the triplet state is in the higher orbital state, delta E, the energy splitting. In this case, for a double dot, it's not a higher orbital state, same orbital state. The only splitting that you're going to get is the tunnel coupling, splitting due to tunnel coupling. Okay, so there is a crucial difference that you need to remember to understand one of the very crucial phenomena which happens in the double quantum dot system, that is spin blockade. So just remember, the singlet triplet splitting for a double quantum dot system, the 1-1 configuration is not really high. But of course, the Pauli exclusion principle applies in either case. But the singlet triplet spacing for a single quantum dot, say 0-2 configuration, is very high because the singlet and triplet states are different orbital states for that dot. So This we need to remember to understand the discussion that we are going to make further. Okay. After discussing the singlet and triplet states of the single and double quantum dot systems, I think now it is time that we discuss a very important and crucial phenomena in the transport through double quantum dot system, that is generally referred to as Pauli spin blockade or simply spin blockade. It is the manifestation of Pauli's exclusion principle in transport property and happens in a tunnel coupled few electron double quantum dot system in the transport regime of 101120. That means you are starting from a system with 10, then an electron enters and the system goes to 11. Then that electron moves to the second dot, in our case from right to left, and goes to 0. Then finally that electron will tunnel out. Then you will be back to 10 state. That is the charge cycle we are referring to. Okay. So, of course, the same thing can also happen in the opposite configuration where you start with 0, 1, 1, 1 and 0, 2. But that you will see that will happen at a different bias, basically the opposite bias. Okay, that we are not discussing here, but these two phenomena are same. Let's discuss this charge configuration now. Okay. So we have 101120 regime. Here on the 101120 regime. What that means is one of the dot always got the electron. There is one extra electron in all the time in one of the dot in this case on the dot 1, that is the left dot. Okay, and that is represented by the single spin here. Okay, now this is dot 1, this dot 2, and what you need to pay attention here is to the label ST and ST here. So whenever I have label S11 and T11, that electrochemical potential refers to the situation when you have one electron on each dot. That is, this electron stays here and the next electron comes in. Then this is the energy or electrochemical state of the system, electrochemical potential of the system, S11, T11. Okay. Don't mistake this to the energy levels of this right dot or the dot 2. This is the state of the system in the 1 double dot state. Similarly, when I have label S20 and T20, what that means, you have both electrons in the left dot or the dot 1, and this is singlet state and this is a triplet state. So you can see naturally, as we discussed in the previous slide, that this singlet triplet splitting for a single dot, that means when the 2-0 configuration is large. Okay. Whereas singlet triplet splitting for 1-1 state is small. This spacing between these red and green lines. Okay. Now, and this singlet triplet splitting is a function of the dot geometry and the coupling. So that remains same throughout this discussion or throughout throughout the measurement that we are discussing. Okay. Now in the low bias regime, the levels are aligned in this fashion. So you have both singlet and triplet states available on the dot 2 or the right dot, whereas only single state is available in the dot 1 or the left dot, and the triplet state is high up here because it is a higher orbital state that is not accessible. Okay, so the subtle point here is this green line represent the energy level or energy state of system when you have two electrons in this dot. This one electron is already here and that is below this state. Okay, that is already there. That is locked. Okay, you are not referring to this dot. This green line refers to the state of system when you have the second electron comes here from this side or from this side. Okay. Now, at low bias regime, we know that we have only the triple points. No triangles are possible. The triangles comes when you increase the bias. These points will expand into triangular regions. So in the low bias regime, electron with spin up or spin down can tunnel here. If it goes with a spin up, then that electron cannot tunnel here because spin up electron need to go in this region. This is the state corresponding to the spin up 2 0 triplet state. Spin up, a second spin up electron here will make a triplet state with this existing electron, and that energy level is here, which is not accessible. So when you have a spin up state, let me mark that by a red arrow here. This can go here, but this cannot tunnel here because this state takes a spin down state because it's single state. Okay, but it's okay. This electron can tunnel back because in this low bias regime, the level here is in resonance with this Fermi level. This is the drain side according to our notation. So this can go back to the Fermi level and another electron can fit with the spin down. That easily can tunnel in, then that can tunnel in, spin down, and eventually it can go here. So that is possible. What that means is you will have current for a low bias regime as long as this level here is close to the Fermi level. Okay, so you have current, and that is represented by this bright orange spot here. This is the situation when you have low bias. Now when you increase the bias, what happens is you have this configuration. So the level in the dot is somewhat going to remain same, because when you increase the level with respect to this level in the dot also is going to feel that potential. So they also will get lifted a little bit. But that is not really relevant for this discussion here. That is because source dot and drain dot capacitance, that we are not worried. We are not going to worry about that now. But now the situation is slightly different. Assume that you have a spin down electron, because all these things happens in a zero magnetic field. So you have both spin up and spin down electrons in the dot. And our assumption is that the spin flip of this extra electron on the dot doesn't really happen. This spin is fixed. This electron doesn't flip the spin. That is our assumption. Okay. That is true also. Now, assume that you have a spin down electron first. The spin down electron can tunnel here, and it actually can occupy the S11 state. okay, that actually can tunnel here. This will occupy the S20 state and tunnel out. You will get a current. But you have equal probability of spin up and spin down electrons in the absence of a field. You have both states degenerate. So no matter what, in a fraction of time, you will have spin up electron tunneling here. Now, the spin up electron represented by the red arrow here cannot tunnel into the dot 1 or to the left dot, because that state, the green level, correspond to a spin down state. That is prohibited for a spin up electron by the Pauli exclusion principle. The spin up electron need to go to T20 state up here, but this state is energetically not available for that electron. That is high up. Now think about whether this electron can go back and another electron with spin down can tunnel into, as in the case of a zero bias or low bias situation. But now this electron cannot go back because all the states here are actually full. These are filled state. This electron cannot go back. This can go back only to the Fermi level here, close to Fermi level here, but that is also not energetically available. So what energetically favorable? What that means is that electron is locked forever until this electron makes a spin flip. Okay, but then that electron can escape here because now this has flipped the spin. This actually can come here, but no matter what, this then now the spin our down electron is forms a triplet. Again, the same situation will happen and the transport will get blocked. So what that means is the Pauli exclusion principle blocks the transport. This is called spin blockade. Okay. Now think about changing the gate voltage configuration such that you can lift this state here, to bring it, make it in resonance with this T20 state. Then this triplet, the spin up electron and spin down electron both actually can go through, because spin up electron can go through this state and here, and spin down electron can go through this state and here. So the green one can go here and the red one can go here. Both are possible. That means current will resume, and that is represented by this region here. That is when you are going to get current. So in this situation, until you lift the level of the dot 2 to the 20 state, T20 state, current is blocked. So throughout this region, the current will be blocked, and this is called spin blockade. And the current will resume when you lift the T11 state and TS11 state, both in resonance with the T20 state. Of course, you also need to have the source drain bias supporting that. Okay. Then you will see a current flowing through the system. Okay. So in this regime, the current is blocked because Pauli exclusion principle for this biasing condition. Now let's look at what happens in the reverse bias case. Same configuration for the dot. Reverse bias, the spin down electron can go here. Okay, and if it is spin up electron, it's not accessible, but it's okay. It will actually get replaced by a spin down electron because this level is in resonance with the train. Okay, that is the situation when you have small bias. Okay. Now, when you have large bias, both the spin down and spin up actually can go, because these states are pretty close in energy. So that state can, there are two states there, the green and red line. They are pretty close in energy, the green and red lines. They can take both the up state and also the down state in the large bias case. Okay. So in either case, the transport is never blocked in this situation. Okay. So this state can never take a spin up electron. So the spin selection happens here itself, the tunneling itself. Okay. And the spin up electron can actually tunnel when the T0, T20 state is available. Okay. Now, let us inspect what happens in the reverse bias case. The dot configuration, the gate voltage configuration remains same. The bias is in the reverse. Bias is reversed, or the electrons flow in the opposite direction. So in this low bias configuration, only the spin down electron can tunnel, because spin up electron need to form a T20 state. That energy is not, that level is not accessible. So only the spin down electron can go through the system. But anyway, there are plenty of spin down electrons, so you will get the current through the system. Okay. Again, these are all in the single electron tunneling regime, so you will get a current through the system. And when you increase the bias, the spin down electron can go to this channel, S20 channel, and spin up electron can go to T20 channel. So you have both spin up and spin down electrons participating in the transport. In either case, the transport is not blocked by the second dot, as in the forward bias case, because in the second dot, both T11 and S11 states, both are very close in energy, both are available always to receive electrons coming from the left side. So you have no blockade in the reverse bias case. Only in the forward bias case, you see a blockade because of the Pauli exclusion principle. A reverse bias, you will see the full bias triangle always. In the forward bias case, the partial bias triangle is partially blocked. I mean, partially no current in the lower bias regime. Okay. And here are a couple of examples. This is from a silicon germanium double control system, where this region marked by this dashed line correspond to this region here, same as this region here, where no current is flowing through. But you can see the edge, you have the current. This corner you have the current. But that is the low bias case, where you can has been exchanged with the lead. But the moment you have higher bias, that is in the middle of this region, the current is blocked. And that corresponds to this situation. Okay. Around this edge, you can always have a spin exchange. Okay. That is the resonant condition for that dot with the lead. Okay. Now, of course, this region correspond to having a different gate voltage configuration, where this T11 and S11 state in resonance with the T20 state, where the current is going to receive. And opposite bias case, both these channels are available, and you get no block. You have no blockade, and you get current through system all the time. And this is the spin blockade in the forward bias regime. When the biasing condition whether it's forward or reverse depend upon how the dots are configured. But in one direction you get no current inside the triangular region. The triangular region should look something like this, okay, and you have the triple points, okay, that's how it's supposed to look, okay. In the opposite range, or in the opposite bias, you have the full triangle available, okay. So in the one direction you have no blockade, current is flowing through the system. In the other direction you have transport blocked because of the Pauli exclusion principle. This is in a different material system. And in summary, what you are seeing here is the Pauli selection rule applied to the transport system, okay. Now, just to summarize and close this discussion, let me make the following statement. The Pauli spin blockade is a recipe to relay spin to charge conversion, because here the charge transport is blocked because of the spin selection rules. Now, why I am saying it is spin to charge conversion? Because this whether the state has spin up or spin down, it's going to affect the transport through system, or it's going to affect the tunneling of electrons from one dot to the other dot. So just by detecting that tunneling event, or the presence of that tunneling or absence of that tunneling event, is going to tell you whether what spin state the dot got, or what spin state the electron got, okay. Or you can tell whether the system is in the 1-1 singlet state or 1-1 triplet state. And in the quantum computation, one of the quantum computation architecture using electron spins in quantum dots, you have this singlet and triplet states as the basis states, where one is the state 0, another one is the state 1, okay. Zeros and ones are the singlet and triplet states. So you can tell whether the system is in the singlet state or a triplet state by observing this tunneling event. And this is more of a blessing, because the detection of single spin is really hard used by probing its magnetic field or magnetic moment, because it's a very tiny amplitude. It got a very tiny amplitude, and it's almost impossible to detect. But now this spin blockade is giving you a lever or handle to detect what is spin state by observing the transport, because the spin state is up or down depending upon which way the fixed spin is aligned. The transport happens or gets blocked. So just by sensing the tunneling event of the charge, the electronic charge, you can tell what is the spin state. So it's a spin to charge conversion recipe. And that is the proposal for detecting the state of a qubit system for the quantum dot spin qubit architecture. So in one case you have no tunneling event, in other case you have tunneling event. And detecting the charge state of a dot is very easy compared to spin state. And that you will see in one of the upcoming lectures. Okay. So you can detect the charge state of this dot. If this says 2-0, then this pin is opposite to this pin in this configuration. Okay. So you can tell with this incoming spin is up or down, or this is forming a single state or triple state with this excitation spin just by observing the tunneling events. The spin blockade is fundamentally really interesting because you are seeing spin selection rules and transport, but it is technologically also really important for quantum information processing, especially for reading out the state of a quantum dot spin qubit.